and we'll be able to do things with it. Okay? All right, so see you soon. My tea is brewing. How many butternut squashes do you have?
Inside, I think I have 28. And actually, you just reminded me, I had like 4 more out there that I need to harvest.
Oh my God.
Because we're going to get a hard freeze tomorrow night. Down in the 20s.
It's raining here.
Yeah, it's raining here too. But like after the rain clears tomorrow afternoon, it's going to be like it's probably going to, the rain is probably going to go until late in the afternoon, but then after it clears, the skies are going to be clear. And so all of the heat's going to go away. And so we're going to see a 20-degree night tomorrow night.
Well, it started snowing here. So
Really? Where are you?
In Ottawa, Canada.
Oh.
Yeah.
Yeah, I have a student whose family is in Vermont. They have a second home and they've been there since the COVID started. And they've already had a hard freeze. I don't think they've had snow yet though. But they had a hard freeze by last week.
Yeah, I'm really sad. It's already dark by 6 and it's getting cold again.
Oh my God. Well, hot cocoa. We're supposed to have strong winds tonight, so we'll see. Okay, so we're back. And so this is another lecture. I mean, this is an actual lecture, but I just wanted to wrap up what we started last time. And oh my God, I never stopped the recording. Great. Okay. Well, there's always video editing. We want to learn about the 7 universal facial macro expressions. I'm sure you've heard of them, and if not, you learn about them. How to digitize facial macro expressions, and how to characterize the digital data using real data. Did I lose Theo? Oh no, Theo is there. Okay. Okay, so those are our objectives today. That's okay, Theo, if you want to have it off. I just wanted you to see this lecture because we want that ganglia causality eventually incorporated in this. So
yeah, which leads which.
Yeah,
basically it links to that.
Yeah, so we've been hammering on this taxonomy of the nervous system up to now. So I'm just going to remind you again that we have afferent fibers, which are mechanoreceptors, nociceptors, and thermoreceptors driven. So these are our sensory organs. And we also have social motor axis in the face and the body. So we have well-developed maps that at some point mature and feed back to the brain and form somatosensory motor maps in the primary somatosensory cortex and the primary motor cortex. And we have created this taxonomy with intended actions, deliberate, staged, purposeful, goal-directed, under voluntary control, unintended actions, spontaneous, supplemental, goalless, uninstructed, and so forth. And then we were discussing these inevitable actions like our unintentional beliefs turn intentional. And so that's kind of, again, food for thought that we were discussing about that last time. So we could revisit that at some point. And the the sociomotor axes are driven by well-defined maps that feed back to the brain. So from the, for example, trigeminal nerves innervating different parts of the face, and from different parts of the body that are well divided topographically. So today we're gonna focus on the face and the characterization of the 7 universal facial microexpressions. And so we're gonna use that software, OpenPose, which I hope that you can install and so we can play with it. Otherwise, I will provide the MATLAB process data, but it's better if you actually do this yourself, because then you can do it at home. So we need to think about facial output and facial feedback. So all these nerves that innervate the face and the muscles and so forth, these are the facial nerves. And it's a very complicated network, but it controls our eyes, our hearing, our mouth, and has a lot to do with a lot of the different, even swallowing feedback from that, but speech perception and reception and so forth. We're focusing primarily on the facial microexpressions, but also combined with sound, the audio that we collect from combined video and audio. So the audio also, you will see the audio contributes to these emotional and facial characterization. And so one thing that might be nice to do in the class is collect this information through Zoom and then process it, because Zoom saves both the audio and the video. And so we can both get the micro expressions of the 7 universal emotions through the visual domain, but also through the auditory domains. We can have a characterization of ourselves. And I would like to have that as a group and also individually, like you do it at home, because it's different. It's bound to be different. So we can actually test that hypothesis, whether it's different when you do the 7 micro expressions on your own at home versus when you do it here in the group. And I can tell you in the group, trying to do this staging a pose of an expression versus actually doing it, it's a lot of fun, but it's also tricky, because in a group, then we're influencing each other, whereas when we're at home, you actually do it in a cleaner way. But we can do both and characterize them to look at the differences. So we have efferent nerves that bring output activity to the muscles from the brain, so the efferent information output. Afferent is input, nerves bring input back to the brain. And we have 2 kinds of reafferents: endoafferents, which are self-generated afferents via self-generated micromotions, and exoafferents, self-generated motions via external micromotions. For example, vibrations, if they are directly physically done, or mirroring, automatic mimicking and mirroring that we perform. When producing an emotion, because of these closed feedback loops, by mimicking its microexpression, you feed back and evoke a memory of that emotion, thus evoking its actual sensation, as if you were experiencing it. Even though they're unconscious, bringing them up to consciousness can help training the emotions. This is important in social interactions, for example, to train to perform good job interviews, or to, in general, blend in. And I'm sure it's something that, I don't know, psychopaths have it down quite well, because they end up fooling people and so forth. So some links, let me see if we can go there. Yes, can you see these? Atlas of Emotions? No, because I have to, hold on a second. I bet let me stop sharing and make sure that I share with computer. now. Can you see it?
Yes, but it is showing the, well, no, now we see the slide again, but it's showing the presenter's notes and stuff.
Okay, one day I will get this right. Let me see, where is that one? You see the presentation, right?
Yeah.
But I also wanted to go and show you that. Can you see it?
You see a gray screen right now?
And what?
Anybody seeing anything other than a gray screen?
No, I
Yeah, I
just,
see a gray screen, but I also see your cursor, a
Yeah,
hand cursor.
Liz, before it showed up, but it looked like it was dragged off screen.
Okay, let me just share that, and it's easier. Do you see it?
Yes.
Yes.
So this is Paul Ekman's map of emotions.
Is it really blurry for anybody but me? Like
It is blurry.
Yeah. Oh, it's better now.
Yeah, there it goes.
Yeah, I just wanted to see that, like, if you click on, say, anger, and so then there is a map of all the different, so there is anger, but under anger, there are all the things that evoke like annoyance, frustration, exasperation, and so on, and then fury. And they have kind of representations of intensity, levels of intensity. These are all things that we can study, by the way. This is all for grabs. There is fear, and it has different, again, different disgust. And I bet that we could think about different sensory domains that could drive, you know, some of these things.
Liz, why are the shapes different? Like the shapes of
I don't know, actually. I don't know. It's a good question. I just became acquainted with this site like yesterday. I think I haven't actually navigated it. Let me see what else.
They look like different distributions. They look like different distributions.
Yeah.
Yeah, I don't think is so this is his home group, and they offer some training, of course, for a price. But I mean, it's fun to navigate, and they collaborate with a lot of people. But interestingly, they rely a lot on eyeballing the whole thing. So it's, there is room for this kind of stuff we do here. So let me do that again. I know that I have some other, like, I mean, there are very, very nice interviews with him. I won't get into it because I don't want to take away from the time, but this is for your own, like, when you go home and stuff, look at it. It's really fascinating. But what I found is that, so he's written like 15 books or something. Actually, there is another link here. Hold on. Yeah, so this is a nice link I included in the presentation that has kind of information about a lot of what they do. He's older now, so seems like a little bit more fragile. Hold on a second. Let me go back to the and share again. Okay. So here we are. And we went through all of that. Yeah, so I put these two links so you can, you know, Google some more. And so what I didn't notice was a lot of the type of statistics we're doing and so forth. So I think that that's a good thing that we could actually do some more. So we want to get from the macro level of description, which is pretty much what I've seen, to the micro level of stochastic and dynamic synergies analysis. This is the website that I just showed you. And he read a lot of the Darwin stuff that related to facial universal expressions and so forth. And that's how he started the whole research on this and traveled quite a bit and came up with it. So it was all inspired. So let's listen to this researcher, Vanessa. I can't remember her first name, but the last name, but she'll say it.
I'm Vanessa Van Edwards, and I'm a behavioral investigator. Today, I want to talk to you about the 7 universal facial expressions. Dr. Paul Ekman is the one who discovered that our facial expressions show our emotions. And he discovered that across genders, across races, across cultures, there are 7 universal facial expressions. I think that when you read these facial expressions, you can discover and detect the hidden emotions under the words. So you ready to learn them? Let's start with the first one. The first one is disgust. So disgust is the face you make when you smell something bad. So you can try this with me if you want. Just show the upper teeth like this and crinkle your nose up and make that gesture. That is disgust. Now, people make this not only when they taste or smell something bad, but also when they don't really like something. So if you ask a teenager or a friend, hey, what do you think of that new girl? And she's like, you might know what she actually thinks before she says something. The next one is anger. So this one is really important to know before you get into a big fight. Anger is when you see these 2 vertical lines appear between your eyebrows. So with me, if you can pull your eyebrows down and these 2 vertical lines appear, and then harden your lower lids and tense your lips. That is an angry microexpression. The funny thing is, when you do it right, you know you start to feel just a little bit irritated. That's called the facial feedback hypothesis. So not only do our emotions cause our face, but our face also causes our emotions. The next one is sadness. This is the hardest microexpression to fake. So ready? Try it with me. This time we're gonna make a frown. So take the corners of your mouth and pull them down as far as they're gonna go. Then I want you to puff out your lower lip. Even if it quivers, that's really good. Now pinch the inner corners of your eyebrows together so it looks like this. If you start to tear up, if your eyes start to water, that means you got it right, because that is the precursor expression to crying. The next one is happiness. It's my favorite microexpression. So most people think that happiness is just a smile. But actually, the only true indicator of happiness is when these upper cheek muscles are engaged. And only 1 in 10 people can consciously activate those muscles. So what I want you to do is make a smile, and then I want you to go as far up your face as you possibly can, so you get these nice apples in your cheeks. If you really want to feel it, you can put a pencil in between your teeth and spread your cheeks as wide as possible. It looks like this. That's that nice engagement. You'll know a fake expression, a fake happiness expression, if someone goes, yeah, I'm so happy for you. But that smile never quite reaches.
Oh, shit. Sorry. Are you hearing this?
Yep.
Okay, good. All right.
Do our emotions cause our face, but our face also causes our emotions. The next one is sadness. This is the hardest microexpression.
Okay, we saw that one already.
Then I want you to push the inner corners of your eyebrows together. That means you got it right, because that is the precursor expression to crying. The next one is happiness. It's my favorite micro expression.
Oh, we did that too.
So most people think your face as you possibly can. So you get these nice apple teeth and spread your cheeks as wide as possible. It looks like this. That's that nice engagement. You'll know a fake expression, a fake happiness expression, if someone goes, yeah, I'm so happy for you. But that smile never quite reaches their eyes. The next expression is fear. So fear is what we do when we're trying to protect ourselves. So let's say that you're hiking in Forest Park and you see a snake. Your eyelids and your eyebrows jump out of the way so you can take in as much as you possibly can. So you open your eyes really wide, you open your eyebrows, and then you go, that is the fear expression. So when you hold that fear expression, you're able to take in oxygen in case you have to fight or flight, and see your environment around you. So you pull your eyebrows up and widen your eyes, you'll actually begin to feel a little bit anxious. The really close micro expression to fear is surprise. Surprise is a little bit different though. You raise your eyebrows as far up your forehead as you can, and then you drop your mouth open. It's the longest of the micro expressions. So it looks like this. So watch the difference. Fear has flat eyebrows, whereas surprise has upside down U's. Watch, this is surprise, and this is fear. That's really important for parents. If you're asking someone, did you know about that incident at school? The difference between no and no is a very, very different set of questions. The last one is contempt, and I think this is the most powerful of the micro expressions. It is simply a one-sided mouth raise. Looks like a smirk. Either side of the mouth, any kind of asymmetry means disdain, pessimism, or hatred, and it's the one you really want to watch out for. So if anyone says something positive along with that smirk, you know you have something to watch out for. Here's a little test for you. Now I want to see if you can guess which micro expression I'm doing. Are you ready? Those are the 7 micro expressions, and I can't wait for you to start seeing them in your own life.
Isn't that neat? So last night, I decided to actually digitize them and applied our gamma micro-movement approach to see if we could differentiate them or what happened. So here's discussed, and she describes like how to get it. So what ideally would be nice is that we all did it, like follow this recipe, and we did it. So this is the digital version of it using OpenPose. I was able to extract it. This is anger, and this is sadness, happiness, fear, surprise, and contempt. So this is the raw data that we get. These are pixels per frame, and the frames that we get from, what I did was I edited the movie, cut it, I cut it, the parts where you can clearly see each one of the micro expressions that she's describing. And you only need a few frames to do that. And so this is happiness and this is sadness. These are the micro movements derived from it. For the 3 regions of the face that I explained before, which we divided the grid into V1, V2, V3, these are the gamma signatures extracted from them. So each one of them has a different signature, and they change the V1, V2, V3. So remember, V1 is like the eye area, and this is the mouth, nose area, and this is the overall line of the face area. And so they're different. You can see that the distributions also are different. And here's where they fall on the gamma parameter space. So interestingly, anger stands on its own. I mean, each one of them groups differently, but there is a clear division here between anger, disgust, and happiness. And then there's other ones over here are contempt, surprise, and sadness. And so the one thing she said was surprise and fear were close together. So where's surprise? Over here. And where is fear? So surprise is over here and fear is over here. So they are indeed closer. But the rearrangement of the face areas is different. So that was actually quite neat. So one thing I would like to do is for each one of us to characterize our own 7 microexpressions and plot it and see where we fall. This will be a characterization of that. So then let me go a little bit over pose estimation very briefly, nothing in detail because it's all online. You can read about it, and I just want you to get a sense for what we can do with it. It's free software from Computer Science and Carnegie Mellon. And what I would like to do is install it in your PC and process, collect video data from yourself or from others, and have an exercise on faking microexpressions versus trying to get a spontaneous, so staging versus deliberately staging a microexpression versus spontaneously getting that. And you could do it like maybe with a joke, fake a smile versus actually laugh. We can make these faces to generate a data set and process the movie to isolate the frames and so forth. Run OpenPose to get the skeleton, the grid, and then do our stochastic analysis and try to classify different things about it. So we could play with it and then do this at home on your own when you're not in a social context to create the same data set and see whether how different we are within a social setting versus alone. For example, we could make these faces and generate the data set. We could do this by generating the faces of a spontaneous type of situation versus staging it, and then we do the analysis. Okay, so then we would like to have individual presentations so that you could present your results and then we could discuss as a class. And I'm proposing to account for 20% of the grade. This is also negotiable. I mean, if you want to do something else instead, it's fine, but I think this would be fun. Okay, so then let's do network connectivity analysis in an interacting group. So and this is big thanks to Joe Vero, because he was the one that introduced us to OpenPose. And, so here is an example of what you can do with OpenPose. So it's pretty stable. Although it has problems like other arms could get in the way and so forth, but we've been using it in the lab to extract data at home from people under like a clinical trial we're running. And so that's an interesting thing for the body. For the class, we're just gonna do the face. So essentially, in a nutshell, builds body heat maps of the body parts that are most likely to fall together. And it builds those models through machine learning training. And for the face, there are 70 key points that we can take. And it can also, it also has a model for hand detection, and it has a model for full body kinematics. You give an input as an image as input, and of course it's a series of images because it's different frames, and it computes these heat maps. It uses different techniques for vector fields and flow fields and so forth, and combines that with just logical information like your elbow likely follows the piece that starts at the shoulder, and your wrist follows that other piece because of continuity of the body biomechanics and so on and so forth. And so likely the hand is over here and not over here, which would be another piece and so forth. So in the blind, you can begin to estimate this and statistically make sense out of it. And so it builds a heat map of confidence of different parts and builds these affinity fields, which just means that there is some preservation of certain properties and certain geometric properties, and represent the best matching orientation of the body part. So then there is a whole bunch of under the hood machinery for adaptation and learning of that affinity field map. And at the end, you come up with a kinematics representation, a skeleton representation. And in time, you get the trajectories and the kinematics. So if you want to learn more about the actual OpenPose algorithms, I encourage you to go to their website, and it's very informative. We're using, in this case, the facial representation, and we have divided it into these V1, V2, V3 based on the physiology. It's a nice way to extract emotional information, non-invasive. You don't have to interfere with trackers and so forth. It's cheap to distribute, so it's free for academia, so we can all play with it. And we can check on our own work. So it's repeatable and it's easy to set up. So here's an information of what we did. This is a neutral in a Zoom lab meeting. This is a neutral configuration. So people are just kind of there doing the neutral thing. And this is everybody saying what they have for breakfast. So we're just there not doing anything. It's our baseline configuration. And this is us saying.
I had a banana and yogurt and a bunch of fruit and coffee.
Anna?
I had peaches and yogurt and plums and coffee.
Mona?
I had avocado toast and coffee.
Joe?
I had a bagel and juice for breakfast.
Elizabeth?
I had Raisin Bran Crunch, blueberries, and coffee.
Hannah?
I had 2 slices of bread, an egg, and milk.
Harshit?
A coffee and cheese sandwich.
Theo?
I just had coffee.
G?
I had rice with beef and then a croissant as a dessert.
I'm jealous. I still remember that.
Giuseppe, I had like a latte and biscottis again. That's what I always have, which I share with my dog. All right. Okay, so that was our, and then we had another session. So we had the neutral, we have fake smile, and then we had the social interaction one. So I did all these methods, and so I first cut the data so that we get a representation of the entire Zoom, and then I crop each individual participant in each condition, and this can be done with Clidio, cut video and crop video. You just deposit the video there and download it when it's done. And you keep this order because in that way you keep everybody synchronous. So if you crop first and then cut later, it's going to introduce error. So you want the timing to be synchronous. So the other thing is the audio. It's in this case you had the audio saved. So this one is just the neutral condition. So there's no, and this is the fake smile. Okay. And then this is
I had a banana and yogurt and a bunch of fruit and coffee.
Anna? So you can see Richa when she's talking about herself, what she had, but also when she's listening to everybody else saying that. Mona?
I had avocado toast and coffee.
Joe?
I had a bagel and juice for breakfast.
Okay, I'm gonna advance to G.
I had like a
no, G is like
croissant as a dessert.
I'm jealous.
Anyway, so the important thing is that we have the person's speech, but and everybody listening to it, and we had so we can look at that progression for each individual.
I had a banana.
Did anybody ask a question? No. Okay, so here's here's the division of each area, and like for example, neutral versus smile.
I love the chart titles here. I love the chart titles here.
Oh.
Neutral, fake, breakfast, Richa.
Well, I mean, it's just, yeah. So this is everything, because it's everything, neutral, you know, and I should have used different colors, but this was last night, so I was kind of sleepy and I already tired and doing busy other things. But so the idea is that if you focus on each one of these parts, V1, V2, and V3, you see the changes. You see that they change with each condition. And of course, this is bad because I should have marked which condition was what, which could be done with the edge of the marker. And I'll fix that. But for now, I just want you to know that, for example, if you go to V2, which is like the smile region, you see how it changes a lot. So it changes from neutral to, and then jumps up to the social thing. So, and the same, we do the representation of the gamma parameter moments space, and we see also the changes. So this will be very nice to plot in trajectory form so that I can join the lines of each one of these so you can see quantify the change, and then compute the air mover's distance and bring a different representation. Now, this is everybody. This is an adjacency matrix for everybody. So this is actually 690 by 690 entries. Each person has 69 by 69 matrix. And this is the person Width itself, the similarity matrix here is built with a maxima cross coherence. And at maxima cross coherence, we compute the maximal phase shift and the frequency at which this happens. So this is that representation for the fake case. And you see the cross coherence is not very high. So it's not, it's about 0.4. And you see, but you see some patterns for in Elizabeth's face and Hannah and Mona and so forth. Then this is the fake representation, and now already jumps between 0.5 and 0.6, sometimes 0.7 in some places. And it acquires a structure in certain people, and you can also, and then this is the social interaction. So now you can see that it jumps much higher. So it actually has higher cross coherence. It really highlights a lot of the patterns. And this one was done with the sound. So in each one of them, the person is listening to the other people and to what it said. And so yeah, and so these are the frequencies. So I have a lot of low frequency. So I must have like tremor or something in my face that this is capturing. And this is like you can compute at zero lag the perfect synchronous information. I didn't include that here, but I included in the next one. So neutral versus fake. So you can extract what at zero lag what's happening. And so these are the patterns, total synchronization for each individual person. I also did it for the whole group, but I forgot to include it. But you can see that we can quantify a lot of things using then this representing this as a network, as an interconnected dynamically changing network, and compute different connectivity metrics. For example, this is the clustering coefficient, which again gives you a sense of the node and the neighboring nodes level of connectivity. And you can see how it changes for the neutral, the fake, and the breakfast case. So there are 69 entries in each one of these scalar values, and you can see how they change for each person with respect to the fake or the neutral condition. And these are the distributions of the degree distribution, which actually tells you something about the topology of the network. And so if you have a distribution like this that is more like an exponential type, this represents random networks where every node is likely connected to every other node. So there's a lot of, there's no pattern emerging. And but what you see here, and as the distribution changes shape and it starts approaching more of a Gaussian, then it means that it has hubs. It has hubs here at the tail, and it has more structures. So the hubs are the subnetworks that form, self-emerge, and that happens in the social in the social context here. To a certain extent, in the fake condition happens, it starts already shifting the distribution. So this is very interesting. Actually, we've never done this before. And then the modularity of a network tells you the subnetworks that form and have maximal connectivity within that network and minimal connectivity with others. So it's the community structure that self-emerges. And so this is the representation of that, but you can bring that to a different representation where you count for it. So this is the modularity. So that this network has up to 22 modules. And these are the 69 nodes of Anna, the 69 nodes of Elizabeth, and so on and so on. So these are the 690 nodes of the network plotted by each individual and the changes. So one thing you can do is evaluate the node participation in each, so you go through it and count the node participation in each module and plot that. So this is nodes 1 to 69, 70 to 139, and so on. How much this node participates in module 1, how much it participates in module 20, and so forth. So you can see that these modules have more participation than these ones over here. And then so what I did next was to actually sum up and so what you can see here is, first of all, for the neutral, you see that they're more distributed as congruent with a random network where everybody's kind of connected. There's no modularity to it. But by the time you get to the social, you see a modularity is clearly emerging, and each person has a clear pattern here that emerges. Except for Theo, and Theo didn't talk a lot. So Theo only talked when he says, I just have coffee. And then he talks again when G's laughing and says, I'm jealous. And that's all he says. So he doesn't talk much. So his is more distributed than everybody else. Then you can sum up that information. And for each node, you plot for each module, I'm sorry, you plot the value of the participation of the nodes for that person. So each person has 69 nodes participating, representing each one of the nodes of the grid. And so you can see the pattern self-emerging. So very different when you have a neutral phase versus when you're faking a smile versus when you are actually socially interacting and listening to people. I wanted to show you other applications. Any questions so far? We're almost done, actually.
For the previous figure, what did the network modules represent?
So they're like synergies within the network. It's like sub-networks. So they are like, this is a 690 by 690 nodes. And imagine a case where each node is connected to every other node versus the case where you have sub-networks of nodes that are like hubs and attractors, and they form a community. So it's like a network heavily interconnected, a sub-network heavily interconnected internally, but sparsely connected with the others. And you can see that here emerging in so these are the modules. You have 8 modules instead of 22. So you have fewer number of, and each one of them has like an attractor. So what we see in the breakfast condition is that each module actually represents like a person. So module 1 here is Mona. Module 2 is Anna. Module 3 is Elizabeth. So each module is actually being taken over by a person, and it's when they're talking and so on. Except for Theo, because Theo was distributed. He was not really talking much. He was more like listening to everybody, which I find very interesting that we can capture that. Is that clear?
In that situation, is it thrown off if you have, like I have a 2-monitor setup here. So my camera is on my laptop, but generally I put the, like I generally put the presentations or whatever on that throws off any of those.
Yeah, I mean, it's very sensitive. So it's the video, it's very sensitive to lighting conditions and things like that. So we have to, when we use it, we have to be try to be uniform, facing the camera and so forth. But even there, with your limitation of the camera, your face was extracted.
Yeah.
Yeah, so long as we can extract the face with OpenPose, and see the variations in these conditions, it's useful to collect the data. Now, what it means, we just begin to scratch the surface because the methods out there are not like these. So literally last night I plotted this thing and I was like, wow, look at sadness and happiness in different planes of the gamma parameter space. And also this modularity figure, like it reveals each module pretty much is the person doing the talking. But that's when we had audio. So let me just show you. So another thing that I wanted to show you has to do with this. Let me see.
By the way, I turned my video off because I keep dropping it.
Yeah, don't worry. So let me
out of the.
No, I kind of I stopped sharing, I think, right? Yeah, I stopped sharing. But let me share the screen for this. So this is really neat. Can you see it? MIT News?
Yeah. Yeah.
Yeah, so this is a new, they've been developing this for years, but it's like a simplified version of the MC10 for those of you in the lab. So this is far more, it's like very thin material, and it gets on the skin. And these are piezoelectric sensors that capture very minute micro fluctuations. And so you can put this on the face, and what they're doing, you see? So what they're doing is they're tracking these micro expressions, and they're using it to develop a map from these gestures to words so that people with ALS can communicate. So they have mapped, characterized, and so this is a patient with ALS who no longer talk, but he can still move the face muscles because the body's going first. But anyways, I wanted you to see that. And lastly, can you see the presentation? Can you still see the presentation? No.
Yes.
Yeah.
Yes. So the last thing, oh, I went to the end. So the last thing I wanted was to show our exercise that we did when we were playing with this. So this is us doing, and this is where we transition from faking it to actually sensing it. So let's see. So that's neutral. Okay. And here we're gonna stage like an exaggerated expression, but then we get ourselves into trouble. And this is like contagious. This is contagious. Like we were there trying so hard, and G's like, I mean, we couldn't hold it. But I'm now going to analyze that data. Unfortunately, I don't know where I put the audio. I mean, I extracted the stuff. I had to find where the audio went. But in essence, we can do this ourselves. Actually, you know, I downloaded Donald Trump and Biden, the last debate. So there is this part where he says something about the audience, like when he's asked about Black people, and he's like, yeah, and this dark, but I don't care.
Yeah.
Oh my God, I couldn't believe he's so out of touch, this guy. So,
yeah, I remember that.
Anyhow, I'm going to analyze the face during this thing. So it's a lot of contempt when he's talking. So I want to quantify the amount of contempt that he has and disdain for the people that he's telling what he's telling to.
I'd like to see, like, I'd like you to do that for one of his rallies.
Yeah, I can, if I get, like CNN has a lot of, or Fox, like actually I got this from Fox News. They cover him broadly.
Yeah,
so
covering his rallies anymore because they realized he was using it for free advertising. But I would like to, I mean, I'm sure that like their internal campaign is covering it or whatever. But I'd like to see like his micro expressions at one of the rallies, because I'm sure that we would find that he was disgusted and full of contempt for the people who show up.
Yep. I mean, the contempt one is one that you cannot hide. I mean, it's so there. So, and that's what he has for everybody. Disdain, contempt. And that's what I want to quantify, because now I know I can do it.
Right.
So, yeah, this was fun. So how many people are up for doing it?
I got my hand raised, but you can't see me.
Okay. If you guys, Kylie and JY, don't worry about it. Like we can walk you through it. You're auditing anyway, so it'll be very good for your research actually at some point. So we'll walk you through it. But so for all of us that we want to actually do it. So, and by the way, I don't want to put any pressure on the grades. It's just nice to have a goal, right? So like, okay, it's going to count towards. But let's do that. Let's, if you don't want to do the 7 micro expressions because that you think that's too much, then pick one and have your loved one show you. Like Richard did this for G's paper, right? You did the faking the smile and then the actual smile, the actual laughing. And that was fun. And Mona, G and I did this thing. So we tried to fake it, but we ended up in trouble. So try to do it. Discussed, you could smell something bad or something. And then, so how many people have this installed in their PC? Like Joe installed it.
I have a Mac, so I don't think I can have.
No, you can't. No, with a Mac you can't.
And Joe also said you need a GPU for this?
Yeah, you need some hardware requirements. But what we can do for those of you who don't have it is make the videos and we just run it and create the MATLAB structures that have V1, V2, V3.
Yeah.
And then give that back to you if you can't, if it's too complicated. I just think it's nice to have it because then you can do it like I'm doing it. Like I didn't have it in my machine and then Joe installed it and then it's like I did a lot with it. And Richa is doing the babies. Like Richa got the model for the baby and she's working on that. So it's.
And we're doing it for the other project right now too.
Yeah, for the Silas, right?
Yeah.
Yeah. So anyway, so that's pretty much today's class. Any questions or thoughts that you want to do with this? I mean, I'll go over the network in the next class. I'll go over the code and you need to download. So you need to use Clidio, which is free. Like we bought it, but it's actually free if you're gonna generate the videos. And then so just generate the videos. If you don't have OpenPose, we can you just put it in box and I'll process it and upload it and tell you okay the data's there. And then we can go. You need the brain connectivity toolbox, which is free. And that's it. The rest I did. The rest is code I wrote. So I just share it. And And the next step, I want to work with Theo on the ganglia causality. So let's do that.
Do you have some time to?
Yeah, after we can talk. Yeah.
Yeah.
Because then we can put directionality on who's leading in this modularity result, who's leading who. And we can test these things, the things that we can create the ground truth to test all of it. That's what's fun.
Yeah, with the universal expression.
Yeah. And so, yeah, that's why it's so important, because like say that we get your universal micro expressions. This is the exercise I want to do. So you guys characterize your universal micro expressions, and then we have you say something, you know, like in a longer movie, and then we can automatically try to localize where you're sad, where you're angry, where, you know, like in dynamically in a trajectory, in you know. So since we have it, it's something we can, because this is all done by hand coding now, but it doesn't have to be. Like we can automate it totally.
Yeah. I was wondering another thing, like Amazon services and a lot of Google as well, I think, has a face recognition software that recognizes expressions. And I was wondering how are those different from using OpenPose in this work? We used to use, so what Amazon has is a play and plug, where you just put an API entry, you send them the streaming video, and they give back the results in a JSON format telling you, oh, right now the expression is smiling, 90% smiling, 50% disgust, things like that. So I was wondering if anyone has an idea of how that they do that.
I think they do it with machine learning.
Yeah.
Yeah, so that's the difference.
About the OpenPose?
No, not OpenPose, Amazon services. I think they have a neural network trained on that stuff.
Yeah, so that's they train neural networks. They tell you, so you have to, like, one of the problems that we have with this face recognition stuff, for example, is that for the longest time, Black people were not being processed. So the errors are enormous, and the police was using this to profile people and, you know, profile the wrong people and so on and so forth.
They extract features like distance from nose to upper lip, small angles, like universal things that distinguish, that we use in our memory to distinguish people from one another, and they make like feature vectors, like it may be distance between the eyes, ratios and stuff. They put them all together.
So one of the differences here is that you're truly personalizing, in that we get the universal micro expressions of you, and then can detect it dynamically in your own, you know, movie of yourself, and detect when in the movie you're happy or sad or whatever. I mean, in principle, that's what we can do with this.
The problem is these people enforce normal distribution. Like they take, what is the average distance between the eyes? Let's throw a normal distribution there. And
exactly. So it's average, it's population average, whereas here it's truly individualized, personalized, and I mean, it's just fun. I mean, I'm sure they're super rich and all these, and, you know, and my little algorithm here with 2 lines of code is nothing, but we're having fun. I mean,
yeah. No, I was just wondering what the algorithmic differences are.
No, it's just
this might probably be a computationally better way to do it, even.
Because,
this might be a computationally better way to do it.
I suspect that is the case.
But if you rely only on your computational power, you're not improving the algorithm. You need the difficulty. You need the difficulty.
Plus, I think this is one major advantage for something like this is possibly that it allows a better insight into what really is happening than a black box neural network model,
Yeah.
which is like, okay, it gives me the result. I don't know why it gives me the result.
The thing is that
Yeah,
maybe
here you know what's happening, and you know exactly what went into it and what came out of it.
Yeah.
And so you can actually, it's very powerful what you can do with it. But I'm sure that these people, you tell them, I mean, clearly the extreme